All right, here's the general definition for the determinant of an n by n matrix. And this definition is what's called an inductive definition. So in order to do the next step, in order to define the determinant of the next step, you need to know what the determinant is of a previous step. For example, when we computed a 3 by 3 determinant, we needed to know the meaning of a 2 by 2 determinant, right? All of these things involve finding a 2 by 2 determinant. So we needed to know, okay, what's a 2 by 2 determinant? It's that cross product and subtract. So we use that definition in order to define the determinant of a 3 by 3. Here's the determinant of a 3 by 3. Now we need to use this definition of the determinant of a 3 by 3 in order to get the determinant of a 4 by 4. Remember, the determinant of a 3 by 3 is gotten by computing the determinant of the one order smaller 2 by 2. And so in order to define what we mean by the determinant of a 4 by 4 matrix, look, when we compute these 4 cofactors, how are we going to do that? Well, if you cross out one column and one row of a 4 by 4, you will get a 3 by 3. So each one of these things requires taking a 3 by 3 determinant. What is a 3 by 3 determinant? It's this. So we needed to know what a 3 by 3 determinant is in order to compute a 4 by 4 determinant. Now that we know what a 4 by 4 determinant is, we can use that to compute a 5 by 5 determinant. Remember, expanding along the first row, right, we're going to have to use all of these cofactors. But how do you find the cofactor of a 5 by 5? Strike out the first row and any column, and so when you do that to a 5 by 5, you're left with a 4 by 4. So each one of these things requires the determinant of a 4 by 4. How do you do that? Well, that's this definition. And how do you compute a 4 by 4? You'll need to find cofactors involving 3 by 3 determinants. How do you do that? Here that is. So how do you compute a 6 by 6? Well, you need to know how to compute a 5 by 5 determinant in order to do that. In general, let's say we know how to compute determinants of order n minus 1. Well, we will define the determinant of an n by n matrix to be this cofactor expansion along the first row, and all of these cofactors will require computing an n minus 1 by n minus 1 determinant. So you can wrap all of that up in a short form using the summation notation, right? What's moving? J, the column J is what's moving. So we start J equals 1 and stop at J equals n. Make sure to multiply all of the stuff in the first row by the appropriate cofactor. How do you find the cofactor? It's that minor determinant gotten by striking out an appropriate row and or column. Okay, here's that theorem. So we'll let A be any old square matrix. And this theorem says that you can compute the determinant using the ith row expansion. So you'll always strike out the ith row, and then you'll strike out columns starting at 1, 2, and then stopping at n. So the ith row expansion, right, always along the ith row, and the only thing that's changing is the column. So column 1, column 2, blah, 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 column n. And then the jth column expansion. Sorry, so this is columns, not rows. So the jth column expansion looks roughly the same, only instead of letting j vary from 1 to n, where we fix the ith row and let j move, let the columns move, here we will fix the jth column, right, so j everywhere, and then we let the ith row move, so 1, row 2, row 3, blah, 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 row n. Okay, let's use this theorem to pick some convenient row or column, and we will compute the determinant now of a 4 by 4 matrix. So we want to compute the determinant of this 4 by 4 matrix, and you can see conveniently there's a bunch of zeros in the third column. So we are certainly going to want to do the cofactor expansion along the third column, right? Because we won't have to worry about 3 sum-ins. So for example, the determinant of this matrix A is 3 times the 1, 3 cofactor. So strike out this thing and then look at the determinant of what's left. 0 times the 2, 3 cofactor, but that's just 0. So we don't even have to worry about that. 0 times the 3, 3 cofactor, don't have to worry about that. And then 0 times the 3, 4 cofactor. Sorry, 4, 3. Right, so I'm going to strike this out and strike out the fourth row. So it's the rows that are moving when I expand along a column. My bad. Anyway, so this is going. So we just need to find the 1, 3 cofactor. So I'm going to strike this thing and strike this thing. So the first row and the third column. And so what's the 1, 3 matrix that we need to look at? Well, negative 1, 1, 2, negative 1, 1, 2, 0, 2, 3, 0, 2, 3, 3, 4, and negative 2. So how do we compute the 1, 3 cofactor? It's going to be negative 1 to the 1 plus 3 power, and then we want to multiply that by the determinant of this thing. So the determinant of this thing is that 1, 3 minor. Remember that. So here we go. In order to compute the determinant of this thing, here's a column with a 0 in it, or you can pick the row with the 0 in it. Either way, I'm just going to go with the column. So I'm going to expand along the first column. So it's negative 1 times this smaller 1, 1 cofactor. So the 1, 1 cofactor of the smaller matrix. And then 0 times the 2, 1 cofactor of this smaller matrix. And then 3 times the 3, 1 cofactor of this smaller matrix. So what is C11? So the cofactor of the smaller matrix. So we're going to X out the first column, the first row and the first column. And so we're left with this smaller 2 by 2 matrix, and its determinant is negative 4 minus 12, which is negative 16. And then we need to remember to tack on negative 1 to the 1 plus 1 power, so that's positive 1. And so this whole thing is just negative 16. So the 1, 1 cofactor of the smaller matrix, that's going to be negative 16. And then next, 0 times the 2, 1 cofactor. Don't need to worry about it. And then next, 3 times the 3, 1 cofactor. So what's the 3, 1 cofactor? So we're going to X out the third row and the first column, and we're left with this smaller matrix 1, 2, 2, 3. So the determinant of this thing is 1 times 3 minus 2 times 2, so 3 minus 4, that's negative 1. And then make sure we tack on negative 1 to the 3 plus 1 power. So negative 1 to the 4th is positive 1, so 1 times negative 1 is negative 1. So there is the 3, 1 cofactor. So here you get times negative 1. So this determinant, A13, right, so we can see now that the determinant A13 is 16 minus 3. So we can see that the 1, 3 minor in this case is going to be 16 minus 3, which is 13. So the 1, 3, and so the 1, 3 cofactor up here is negative 1 to the 1 plus 3. So the big cofactor C13, negative 1 to the 1 plus 3 times 13. So the 1, 3 cofactor is just positive 13. So here we get positive 13. And so the determinant of this matrix A is just 39. So at the end of the day, if A is this 4 by 4, then the determinant of A is equal to 39. So this would be a good final answer for the determinant of this 4 by 4 matrix. Okay, if you're lucky enough to need to take the determinant of an upper triangular or lower triangular matrix, computing those determinants are always easy, no matter what the size of the matrix is. It could be a 15 by 15, it doesn't matter. But if you've got an upper triangular matrix, so everything below the main diagonal is 0, and we don't care what's above the main diagonal, so upper triangular. There's a bunch of stuff up here, we do not care what it is. As long as there's all zeros below the main diagonal. Or if you've got a lower triangular matrix, so zeros above the main diagonal, and we don't care what is below the main diagonal here, so lower triangular. Either way, the determinant of an upper triangular or a lower triangular matrix, it's just the product of the stuff on the main diagonal, right? So product of the stuff on the main diagonal. So the determinant of U, A11 times A22 times ANN. I don't know why I wrote this. And then the determinant of L, same thing. A11 times A22 blah 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 times ANN. Let's just look at a quick example of this. Alright, here's a typical upper triangular matrix. It's 4 by 4. So we don't need to do the cofactor expansion. If we did, we would certainly expand along the first column because it's got all these zeros. And then once we X that out, well, then it's kind of easier to compute. We don't need to do that though. This matrix is upper triangular, right? All of the stuff below the main diagonal is zeros, and so the determinant of this thing is just 1 times 1 times 2 times 3, which is 6. So that'll do it.